Today we're going to touch a very important topic. We're going to discuss about re-engineering. So unless you will start your own business after you get the degree, so 99% of times you'll be hired by a company that asks you to maintain software. And keep the software working. Okay, then it means that you will work on already in place software systems. Okay, it's very hard that you are employed to develop a greenfield software. Then today we're going to discuss about legacy software. What is a legacy software, and then how to deal with this legacy software. So first of all, what is legacy software? Legacy is a software old, okay, outdated, obsolete, or outdated and obsolete. Usually we refer to legacy system or legacy software to whatever software has been produced a few years, few or even more. Many years ago, but still into operation. Okay, that's quite common. In particular, if we think about large organizations, for example, banks. There are many banks that are still using software developed during the 70s. Okay, but also other big companies. For example, there are some. I met recently some guys from the Småland told me that they still have some subsystems in their IT infrastructure developed in Turbo Pascal. I don't know how many of you know what is the Turbo Pascal. It's a very old programming language. Okay. Then this means that some software systems that have been developed many years ago are still into operation. Okay, and then we are still dealing with them. Then it's very important to keep maintaining this software, because if old software has some bugs, then we still need to fix these bugs. So usually, when dealing with legacy system, developers spend so much time working on existing code, okay, than writing new code, because you need to first understand this legacy system. Okay, you need to understand what was in the mind of the developer that wrote that system for the first time. And these legacy systems are still for many different reasons. Can be economic. Okay, it's much more cheaper keeping an old system than developing a new one that we essentially provide the same functionalities, or still because users still need it. Okay, for example, I know that there are some computers that still run Windows XP. Okay, then you might think that Windows XP is a legacy system right now. Yes, it is, but there are still people that use it, and then you cannot abandon the project. I think that Microsoft stopped maintaining Windows XP. They will never issue new service providers, service pack for that type of system. But still, there is people that is still using it. But there's always hope for revitalizing such a legacy system. Okay, even if you have to spend a lot of time, and this is what we want to avoid. So how to, let's say, speed up the process of deal with legacy systems, and how to improve this legacy system. Well, there is still the hope for improving this type of systems. When we deal with this legacy project, it's not just a matter of code base. It's not only the the code that we need to understand. They were projects, okay? Projects that produced the code. But then we need to understand not only the code, but a set of different things. Okay. What the different type of tools that has been used for building the code. Okay. Nowadays we have Maven. Okay, but a few years ago there was not Maven. There was something else, or even before there was nothing. Then code was compiled manually, okay, and all dependencies in the code were solved manually. Then we still we have to understand what was the tool used at the moment the legacy software has been built. The different dependencies of other systems, okay, that were used at that time. The type of infrastructure that was used for the software. Okay, so I mean, if the software was built for Windows XP, then we need to understand the Windows XP. Or if it was produced for a very old Unix system, then we need to know what was this system, how it worked. The documentation. Okay, so the software has been produced within a project, then project usually produced also some documentation. Then we need to learn, read documentation and try to understand how the project was carried on. And the different methods of communication that were used at the time the software has been produced, okay, between developers and the different stakeholders. We need the requirements, the tests, and so on and so forth. So what are the main characteristics of this legacy system? Okay, they are old, of course, because they have been produced years ago. But still we need them. And since they are old, they have been maintained by many different maintainers, many different developers. And each developer has his own perspective on the code. And he has his own habits on how to program, on how to write comments within the code, on how to write the documentation, and so on and so forth. Then it's very difficult to understand this type of artifacts surrounding the project. They are very large, and the larger is the project, the more difficult is to maintain it, because you might have many different functionalities, because these functionalities have been developed by many different developers, because there is a huge code base which is very difficult to understand. You can also imagine, I mean, I don't know, even worse when some non-object-oriented programming languages were used. Okay, now we have a sort of structure in the code, if you think about classes, packages, and so on and so forth. But years ago, the code was not so well organized. There were, of course, many different bugs. Bugs have been solved somehow or patched, but there are still many bugs still exist, because bugs-free software does not exist. There is a high probability of new change cause a regression. I mean, if you don't fully understand the code base, then whatever change you make in the code base, this can affect the entire code base. I mean, you might change something very small in a given method, in a given procedure, and this might have an avalanche effect on the entire code base. Even worse, if you didn't respect the design principles that we discussed during the last lectures. Also, the size of the project affect the type of decisions that you can make on the project maintenance. Okay, sometimes the projects are so large and difficult and risky to replace. Then it's much more easy to keep whole stuff instead of replacing, because I mean replacing can be risky. Okay, you never know if the system that you will produce will be as good as the one that you are replacing, or you never know how much does it cost to create from scratch a new system. Okay, that's why software tends to become legacy. Okay, because they live long. Most of the time, these projects are just inherited by previous developers. Okay, since they are old, of course, they have been developed many years ago and then maintained by many different maintainers. Then this means that I mean, if you start working on this project today, I mean, there's no way that you are able to know perfectly how the code works, okay? And it's very impossible to have the big picture. That's because it's difficult to understand the code written by others, first of all. I mean, I still have some problem now reading my own code that I wrote a few months ago. Because I mean, you tend to forget because you didn't put comments or you just say okay, you leave something to do, okay, and then okay, I will come back later on, but never came back to finish that specific method, and so on and so forth. There are so many reasons because because the code is very difficult to be understood. And sometimes it's easy that the maintainers guess what were the intention of previous developer. Okay, then you are driven by guess instead of saying, okay, that guy did this in this way because this is the reason. Okay, that's why we also discussed about I mean, that every single design decision taken during the design process should be documented. Okay, legacy systems are usually very badly documented. Yeah, exactly. That's the next point. They are really poorly documented. I mean, usually writing documents and documentation about software and about the project is very boring, and then people tend to avoid it or postpone it. And since the development is a continuous effort, then also up-to-dating this documentation is very important. And this is much more boring than writing the documentation. And then usually developers tend to skip that important things. But if you don't document your own code by means of well-written documents, by means of well-written Java docs, for example, if you are a Java developer, and so on and so forth, then it will be, let's say, painful for the developers that will come after you in maintaining the software. But I mean, as software engineers, so what we always focus on is the code itself, okay? Because we always think that this is the much more important part of the project, even if this is not always the case. And usually, this legacy system have not been developed by having testing in mind. Okay. Now we already discussed that testing should be part of the development. So whenever you develop a class, you should also develop the JUnit, for example, part in order to develop for testability. Okay, but this was not the case a few years ago. And then adding tests to retroactively to code that is already written is quite difficult. And then that's why these projects are usually untested. And code is diciamo, let's say often inflexible. Okay, maybe the developers and the designers didn't think about extendability and didn't put hooks for extending the software. Okay, and then a minor change in one specific class or one specific method might involve many different editings within the entire code base. And still, if you introduce a small error somewhere, this error can affect all the code base. It's very important to think about the different design principles that we discussed in the previous lectures. And usually, that's very important. Code in these legacy systems usually encumbered by technical debts. Okay, sometimes, sometimes, most of the times, you are hurry and rush fixing small problems, and then think about, okay, so let's fix this now, and it's not perfect, but it works. It's good enough for solving the bug. Okay. Yes, okay, you hacked something, but this reduced the overall quality of the project. Okay, and then, okay, now it works, but what about tomorrow? That's what we call the debt, because it's just like when you get out a loan. Okay, you fix something today, but at some point in the future you must pay back. Okay, then whatever quick fix you take today is you have to pay tomorrow. Okay, so it's exactly as when you take a loan by the bank. Okay, you take the loan by the bank for buying a car today, nice, but tomorrow you have to pay back the bank. Okay, because they want back the money. That's exactly the same. Every quick fix that you take today without thinking about design principles, about quality, about testing, and so on and so forth, will be paid later on when maintaining the software in the future. And this will go forward, and it can take worse and worse and worse, because you quick fix today and quick fix tomorrow and quick fix the day after tomorrow, and then these are all debts. Okay, and then so at the end of the process there is a bankrupt. I mean, if you never pay back these debts, then your code base it will be really poor quality, and then it will be very difficult to work on it and maintain it in the future. Then it's very important then whenever we fix code and deal with these legacy systems, it's very important to understand that whatever patch or fix we take today can have an effect and affect the future work. Then, if you take too many loans, then you will be in a very bad situation and will agree to and halt the entire project. You get bankrupt. Okay, then it's very important to take this in mind. So technical debt is it's a very important issue and concerns to take in mind. So code is not enough. As we said, it's not only code, it's also the whatever surrounding the code. For example, the buildings, tools, but also the infrastructure is very important. Then usually you spend a lot of time when dealing with the system to understand what was the development environment. Okay, so installing, learning some very old build tool before Maven, for example, that was used when the project has been run. You need to run some very arcane and mysterious script. Okay, for example, written in I don't know if you are expert of Linux, then you have these bash scripts that allows you to make some commands, and then usually are used for compiling very old software, and they are very tricky to understand. And usually you also need a large number of manual steps, okay, in order to understand, for example, how to install a particular driver or particular hardware that has been used for compiling the source code at that time. And there might be some outdated dependencies. For example, I mean, if the software has been developed 10 years ago, he was using libraries and other software that was developed at the same time. Okay, and this software might be not maintained. Then it's very important to, I mean, whenever you maintain a software, to maintain also the different dependencies. Okay, always try to use the last versions or the of the libraries that you use. And there is also what we call a legacy culture. Okay, so sometimes these projects are so complex and poorly documented because people don't like to write documents that you get fear of touching something of them because you never know. I mean, you have to maintain them, but what happens if I touch or a small feature, and then this will no longer this will not work anymore. Okay. Are the bugs safe to be fixed or not? Okay, then this fear of change usually block the maintenance of the software and leave the developers say, okay, let's keep the status quo. Okay, that's the safest option. So never touch things is better than change things that then I have to fix tomorrow because I'm just introducing errors, bugs, and problems. We have to escape this mental barrier, okay? Because otherwise we never get on in our work. So then we have to try to overcome this fear, okay? And we're going to discuss few techniques. Okay, very nice techniques is to just start playing around with the code. Okay, so try to open up the code base that you are supposed to deal with and trying to make changes. Okay, for example, renaming methods, moving methods from one class to another class, try to introduce new interfaces, add the comment as long as you start understanding what the code does, and so on and so forth. This has a double effect to clean up the code, okay, and make the code much more understandable for you. Okay, that is improve your understandability of your understanding of the code and the code itself. Okay, it's like a game. That's because this is an exploratory refactoring. You start exploring the code in order to understand it, but also trying to refactor something and trying to improve the quality of the code. Okay, so the more you explore, the more you understand the code, the more you understand, yeah, the less there is to fear. Okay, you get more relaxed. At the beginning, it's very hard. I know, and you can think about. I mean, overcoming this the fear is very difficult. But the more you try, the more you get confidence, and the more you feel, okay, I understand it. I can make it. Then the secondary benefit that improves also the readability of the code, because you start making more clear, okay? And then you will notice that these improvements are really cumulative. Okay, you start today with something, and then tomorrow, and the day after tomorrow, and then at the end of this iterative process, you will have a better approach, better code base. There is another aspect very important about the software, gathering useful data. Okay, in order to improve the software, we need to measure the software. That's something that already discussed. Okay, then it's very important to gather some measurements and then some data about this software. Then, for example, what is the state? What state is the code to start with? Okay, I mean, you need to, for example, measure the beginning, at the starting point. You measure your software by means of tools. Then you understand what is the numbers of dependency, what is the complexity. You can understand what is the coupling, the cohesion of the software, and so on and so forth. Then you have some starting measurements for the software, and then you can start working it and see if these measurements will improve or not. If you're improving, okay, you're good. If you're not improving, then you need to reconsider the different actions that and decisions that you are taking. Okay, and this allows you to understand how you are progressing in the refactoring and re-architecting, re-engineering process. But of course, first point is to understand and decide what type of measure we need. Okay, well, that depends on what we want to improve. Okay, if we want to improve the quality of the code, if we want to improve the performances, if we want to improve the security. Okay, first decide what is the quality, the type of quality that you want to improve by refactoring the legacy system. Then once you have an idea of what is the external quality attribute that you want to improve, find out the different internal quality attributes. Okay, we discussed this a couple lecture ago. And then once you have the metrics, then you can measure the quality of the software with respect to the specific metrics. Okay, and then start to improve it. So, for example, if we want to improve the coding and remove the bugs, then we can use, for example, static analysis tools that allow us to analyze the code base and detect some possible bugs, okay, or poorly written code. We introduced the last time sonar graph, okay, that allows you to make some measurements, but there are many other tools, okay. There is one is called find bugs that allows you to detect possible bugs in your code. There is another is called Sonar Cube, something like that. I mean, there are many different tools that focus on different aspects. Okay, depends on the specific type of quality that we want to improve. Static analysis also look through the entire code base. Okay, you don't need to do it manually, but you can use these these tools, and they just flag some pieces of code that match predefined patterns or rules. Okay, so depending on the specific language, you can write your own rules or use the already written rules. Also, Sonar Graph has some rules, okay, in his engine that you can reuse or extend by writing new rules. And so the idea is that these tools try to match these rules against the source code, and then telling you, okay, these methods is error prone, and there might be a bug here because you don't initialize a specific variable, or because you are just using a variable which is null and you never instantiated with a new construct, and so on and so forth. They try to match rules against the code and provides you some insight. Of course, the tools are not perfect, okay, because if they were perfect, we would have bugs-free software, and that's not the case, unfortunately. Then they may produce some false positive by flagging some codes as a bug, even if it's not a bug, okay, because they match a rule is static, and then we never know if we have some false positives or not. But they also can point out some false negatives because they fail to detect a real bug. Okay? Then they are not perfect, but they are useful because they provide a good indication. Okay? At least a false positive, it's good. I mean, if we have false positive, but because then you can check and say, okay, no, that's okay, that's good. The tool is wrong. The problem is when you have false negatives, because you think that something is good because passed the test, and then you go into operation and then notice that that specific piece of code that was flagged as good code is a bug. Okay. Well, at least they allows you to pinpoint some poor quality code. That's something that easy to check. For example, the number of dependencies or the cyclomatic complexity for one specific method, and so on and so forth. They are good in this. Bit less good in finding bugs. There are some bugs that are not cannot be found by static analysis. Then, if you want to improve code, you can use this static analysis tool. If we want to improve performance, we need to measure the performance of the system. Okay, and there might be different ways. You can run a performance engineering test by reverse engineering the code into the model and run some analysis. Okay, as you learned in the performance engineering module, for example, by using these queuing networks or Petri nets networks, and there are many different methods for doing that. Or otherwise, you can perform some performance test. Okay, so start the system in a given unknown state, and feed it with data, and just measure how much time does it take to compute that data. Okay, if the time is too long, is not what you were expecting, then there might be a performance problem. Then you try to refactor the code in order to improve the response time.
Using something like JMeter?
Sorry?
Using JMeter, for example?
Well, JMeter allows you to monitor the, for example, how much memory, how much CPU. But I mean, if you're testing, for example, a distributed system, then you need to send the data and wait for the response time. Okay, and then okay, how much time does it last from when I issue the request and get back the result? Okay, JMeter is not enough for this type of measurements. JMeter is very good if you want to measure the performance of some software in your own PC in order to understand how much memory is using, how much CPU is using, and so on and so forth. But for example, if you have a client-server system, then the JMeter is not enough. You need, because there is the network in the middle. Okay, then you cannot measure the network latency by using JMeter. Then you need JMeter for measuring the specific server, for example, but also this type of performance test to understand how much time you need to, I mean, it lasts between the request and the response. And then monitoring, for example, the performances of the system during the production. Okay, so try to log the processing time every time you have a request, for example, to a file. And you put all these times within a file, and then you can just write a script or manually, for example, producing a spreadsheet and then see what's graphically what is the trend of this of the performances. Okay, and then you can calculate percentile response per hour, per day, per month, and so on and so forth. I mean, there are many different ways to do that. Or you can count the error. If you want to improve, for example, the reliability of the system. Okay, I mean, doesn't matter if your code is very fast or not, but what is it's important is that does the job correctly. I mean, if you expect one result and then you get an error, doesn't matter if the error, I mean, you got the error very fast. You still got an error. The result that you are getting is not what you were expecting. Then you got it very quickly, but that's not enough. We want to also measure how many times the software fails. Okay, that's the reliability. So how many times the software fails within an hour, for example, then you can count. Within an hour, I got one error. Within an hour, I got 1 million error. Okay, then this means that the software is very buggy, and then you need to work it out. Then you can count the number of errors. Then for example, catching some exception within your code. So whenever you catch an exception, we can log this exception within a file, and then you can, as done before, you can write a script and aggregate data within the file and calculate some aggregated calculations. For example, you can understand how many errors or exception you catched in 1 hour, in 1 minute, in 1 day, 1 year, and so on and so forth. Then it gives you an idea on how much reliable is the software that we are producing. Okay, and then of course I do it today. Then I try to fix it, and then I will do it again tomorrow, and then see if the numbers of error is decreased. Then it means that the reliability of the system is improving. Okay, if for the same hour the number of errors are increasing, that means that the performance, the reliability of the system is decreasing, and so on and so forth. And then expect your code base, and this is a screenshot of a sonar graph. I mean, there are still many different tools, but we're going to use this in order to understand how many dependencies we have, if the dependencies are circular or not, and other metrics that allow us to understand how good is the code base. So let's have a 10 minutes break, and then we go we go ahead with this decision time. So should we refactor or rewrite? That's always the big question. We don't know yet.
Okay.
Okay, no anticipations on that. Okay, then so let's start over. So now, one big question is always, do we refactor or we do rewrite? What's best? That's always the most important question. Sometimes it's better to refactor, to rewrite, okay, but sometimes it's better to refactor. Even if, for example, we noticed that, I mean, if the project is not too big, people tend to write it from scratch. But if the project is very big, then the refactor is much better. There are some questions that we need to answer in order to understand what's the best way. So, is it possible to improve the code quality, okay, by using refactoring methods? Might be or maybe not. Sometimes, as told you, it's rewriting the system is much easier. Is it faster or easier to throw the code away and write the replacement from scratch? Okay, we also need to consider the time scale. Okay, so I mean, writing and developing a project software in the real world has a cost. Okay, and then we need to take into account the cost for rewriting with respect the cost for refactoring the different code. And then we have to consider some alternative. For example, replace in-house software with a third-party solution. So why keep working, keep producing our own software and put a lot of effort on this software if I can buy the software that gives me the same functionalities, but it's maintained and produced by someone else. Sometimes this third alternative, is the most used. Well, there are some pros and cons for the two things. Okay, as always. Silver bullets do not exist. If you decide to rewrite, okay, this provides you the freedom. Okay, you can do whatever you want. Okay, you are not constrained by previously done design or design decisions, and you can work and develop for testability. Okay, as said. Developing for testability is much more easier than introduce tests for a software that has not been produced for that purpose. But there are some also some cons. Risk. Okay, that depends on the size of the original system. It might take so long to rebuild the system from scratch, and you might need many different developers that work on it. That's something that we need to consider. Some overhead, okay? So usually engineers or project managers always underestimate the amount of overhead involved in setting up a new software project. I mean, you still understand how many developers you need, how much does it cost producing the software, what is the hardware, and we always think that these are easy stuff or easy things. But then we discover during the production of the software and the system that we underestimated this effort. Then it's very important to take this into account. Yeah?
I was talking about rewriting the whole code or just parts of it?
No, from scratch. The entire code. Well, depends on what you mean. I mean, as we discussed last lecture, you can always split one system into subsystems. Okay, then you have to consider the code base of a specific subsystem in that case. Okay, and then you need to understand what's the size and the complexity of this subsystem. I mean, the subsystem is still a system. Then it depends. If you think as a system as a wall, then you have to consider the code base and the size of the whole system. If you takes into account the subsystem, then you have to think about the size of the subsystem, the complexity of the subsystem. Okay, but still, complexity and size are the two considerations. Okay, if the size is very small, and then you say, okay, then this will take very it will be very fast to rewrite it. Okay, and then the rewriting is better than the refactoring. But still, the size, yeah, sometimes size matter. I say. And then always takes longer than expected. You expect to write your system in 5 weeks, and then you discover that, I mean, approaching the deadline, there are so many things that you didn't think about, or so many bugs, and so on and so forth, and then you go over the deadline. Then estimating the time scale is very important. It's better to overestimate than underestimate the effort in terms of time. And then always think that the greenfield software is not green forever. I mean, they are green today, they will be legacy tomorrow. Okay, because of all the different reasons that we just discussed. Okay, then sometimes you may say, okay, I put a lot of effort for producing a new system, for replacing the one that I already have, and then discover that tomorrow you have the same problems. Well, new problems, sorry. Then you are facing the same questions, but with new problems. And then you might still reconsider, should I write or refactor? So there are some necessary conditions that, push you to rewrite instead of refactoring. Sometimes the risk and overhead associated with starting a pure project overweight the potential benefits. Okay, this will push you to the refactoring side. There are some breakpoints. At a certain point, the code base is untractable. And then you say, okay, recovering, refactoring failed, definitely, then let's go for the rewrite of the system. Or because you need the paradigm shift. Okay, today, I implemented my software in imperative programming language, then I want to go for object-oriented programming, then there's no way you can refactor the code. You need to write it from scratch, because this will give you benefits in the future. And there is always a third way, which is the incremental rewrite. You start rewriting small phases, okay? Each individual phase should provide you some value, because otherwise it's not valuable. And then it should be possible to stop the project after any given phase. Okay, in this case you are able to say, okay, let me stop, but whenever you stop, you still have some value, okay, provided by the small phase that you already accomplished. So let's deep into the refactoring side. We say that refactoring is it's an exploratory process. Okay, try and error. You try. If you success, okay. If you fail, you try something else. Okay, but so very important that whenever you refactor, the refactoring should be always safe. Okay, what does it mean? It means that if you are not careful, you refactor and then refactor and then refactor, and then you introduce problems. Then you, in order to solve this problem, you refactor again, but there are other problems, and so on and so forth. And then yeah, you will be out of control in a while, and then it's very mess. we need to throw away everything and start from scratch. Then we need to be careful. Start editing. Yeah, that's the problem. Sorry, that's not the recording. Yeah. So what's up if we have after a while, few refactoring, we have this our IDE full of red crosses. There's no guarantee that the software will still work as supposed to. I mean, because we try, and then we get a mess. So the idea to avoid this situation is that we always try to split the things. So sometimes, most of the times happen that you are fixing a problem, and then, for example, a bug in a method or a class, and then suddenly you realize, oh, why I should split this class in two classes? It would be a better design. Okay, so let me do the two things at the same time. So while fixing the bug, I also refactor the code, because then it's much better. Well, never do it. Okay. It's much safer if you split the two things. First, make the change and fix the bug, then refactor, or vice versa. Okay, you first refactor and split the class in two classes to increase the readability and the quality of the code. Then you can fix the problem. Never do both things at the same time, because if you have some problems, then it's very difficult to understand if the new problems have been introduced because of the refactoring or because the change. Okay, then split the activities. If you focus on fixing the bug or make a change, do it and then refactor. Never do the two things together. And then it's very important to use version control systems. There are many. I don't know if you are used with Git, SVN, Mercurial. There are many different. Whenever you use this, you split refactoring and other change in different commits. Okay, this will allow you to review the changes, to understand when you commit something, if you have committed a bug fix or if you committed refactoring. And very important things, whenever you refactor, lean and trust the IDE. Okay. Nowadays, both IntelliJ, Eclipse, I don't know what type of IDE you use, provide a very nice support for refactoring, renaming methods, adding automatically setters and getters, and so on and so forth. There are very many to indentate the code, to self-document methods and attributes, and so on and so forth. Okay, then use them. They are much more faster than you, because they can deal with hundreds classes in milliseconds. Okay? I mean, if you change one method name in one class, then you have to fix all the classes that use that method. And then if you do it manually, it can take hours. If you do it by using the tool, then it takes milliseconds. They are much safer because, they are not perfect, but they make less mistake than you, for sure. Okay, then use them. They are more trued because, they also do something that you don't think about. For example, changing references within the comments, renaming test classes, and so on and so forth. Okay, they are able to deal with many different aspects that, as humans, we don't think to. And then they are much more efficient. So refactoring is very boring sometimes, okay? Things that you have to change middle name in all classes. That's so boring. They are faster, safer, and they get fun of doing it. That's their job. And still, as said before, make an extensive use of versioning control systems. Okay, this is refactoring is an exploratory experience. You make errors for sure. Then, if you use this type of system, you are able to recover. Okay, roll back whenever you make some errors, and then you discover that the type of refactoring that you want to do is not working, or you are introducing more problems than how many problems you are solving. Then, okay, you stop and roll back and start again. This will allow you to make branches, for example, try different solutions or alternative at the same time. Some of them are very bad, and then you can throw them away. Some others are very good. You get really an improved code base, and then you can merge the alternative to the main track. Then so use these type of tools because they are very very useful in this case. And whenever you mess up with your code base, you can step back and recover from the problems that you just introduced. Where is it? This. Okay. Another really interesting method is this Mikado method. Okay, this is a book written in 2014. If you are curious, I really encourage you to read it. It's a very small book. If you want, I can also provide you. Okay, it's very so the idea is very easy. Okay, you just paper, pen, try to create a dependency graph of the activities that you want to, the things that you need to do in order to improve the quality of your system, and then you execute the task safely and in optimal orders. Okay, whenever you do something, okay, done, done, done. That's very easy and intuitive, but allows you to better understand the sequence of actions that you are taking in order to improve the code base. And still, since this is constructed in an exploratory manner, use this VCS. If something goes wrong, roll back and take a different alternative. Another important action to do here is to re-architecting. Okay, refactoring is in terms of source code, but source code should be organized. Okay, and then we discussed last time that in order to organize software, we need architecture. Then sometimes we need to change completely the structure of the software in order to improve its own quality. Okay, so fixing the bugs in the methods could be not enough. Okay, for improving the quality, we also need to change the overall structure of the system. For example, changing the dependencies between one subsystem and another subsystem, and so on and so forth. Then re-architecturing is just refactoring, but at the higher level. Okay, not in terms of methods and classes, but in terms of subsystems. Okay, for example, refactoring move classes into separate packages, okay, within the same code base. Re-architecting can move classes outside a code base into a different code base, because I said that last time, subsystems should be implemented independently. Then two subsystems have different code base, and then they are maintained by means of different repository. Okay, otherwise they are not independent. Then when we talk about refactory, we just move classes or methods within the same code base. When we talk about re-architecting, we move things and change the structure of the different code bases. That's important. So, but why we want to re-architect the system? Maybe because we want to improve the quality through this modularity. Okay, I mean, we would like to have a modular design out of a monolithic implementation. Okay, we want to extract and make different modules, and then that can be easily manageable in the future. We want to improve the maintainability through good design. Okay, we already discussed about design principles, and then, for example, about some architectural patterns. Then we know that architectural patterns have, I mean, a good impact on the quality. Then, for example, we could think, okay, we have a client-server application, but we want to refactor or re-architect it in a model view controller way. Okay, completely changing the structure of the system. We can increase the autonomy through independence. For example, splitting one code base in many different code bases. Okay, then creating many different subsystems that interact each other in order to solve the problem. One of the most important reasons nowadays is to break up the monolithic application into modules. Okay, legacy systems, since we are talking about legacy system, usually have been implemented as a monolithic way. So one code base containing all the source code for the entire system. Okay, and that's a very bad way of architecting a software solution. We really need to strive for modularity. So then one of the most common reason for refactor or re-architect is to break the monolithic structure of the system and implement it as a modular way. So then the first choice that we need to understand is how to apply the design principle and how to use this, the architectural pattern that we discussed. Okay, that's the most important. So first, we have to decide what type of architecture we want to provide, and then we use our knowledge about design principles and architectural patterns in order to understand what's the best architecture for the system. Okay. Then we can choose different system. This is well, the monolithic architecture. Okay, we have all modules in one code base, and then we have well, maybe one database. Okay, there are some benefits, some challenges, and so on and so forth. Then we want to, for example, split the monolithic architecture in a front-end plus back-end. That's a layered architecture that we discussed last lecture, for example. Then we have the user interface, the application logic, and then the data. Okay. But we also might, for example, choose a a service-oriented architecture where we have many different services that interact each other. And well, this is another course, okay, that you will take next year maybe, if you are interested. So sometimes having a monolithic architecture is good. Some other time is not very good. For example, so nowadays most of the big players, for example, Google, Amazon, Spotify, one of the first to make this choice, is going towards this service-oriented application architecture, and in particular microservices architecture. Okay, because it is the idea of having a lot of modularity increase the scalability of the system, because you can have many instances of the same service that improve the scalability of the system. So, and there are many different reasons. But I mean, there are also some good reasons for having the monolithic architecture. Okay, I mean, so the idea, the choice for the good architecture to choose is always a trade-off between costs and benefits. Then there are some benefits also in monolithic architecture. That's not evil. That's what I'm trying to say. Okay. You never need to make a network call because everything is accessible within the same code base. And then, well, if you need performance, high performance, for example, that might be a key thing, because network, I mean, using the network as a cost in terms of latency, in terms of reliability. You never know what's the quality of the network. If you have a fiber, if you have a Wi-Fi, it's a Bluetooth network. I mean, Bluetooth, having a network between two modules, okay, affect the performances of the interaction. Okay. Then if you don't need the network, I mean, if you need the high performances, then avoiding the network between the two subsystems that are interacting with each other, it's better. Okay. Then usually the system is also fast. Okay. For example, assuming DB queries might be optimized and code doesn't anything crazy. I mean, you might optimize the interaction between the database. Okay, and the development is relatively simple. Okay, developers don't need to understand how to interact with remote systems by sending packets, communication protocols, and so on and so forth, and use the remote API. I mean, everything is under control. This is very good for some things, but is very bad for other things. For example, scaling. Scaling this way can only be achieved by deploying multiple replicas of the entire system. Okay, that's why the big players like Facebook, Google, and so on and so forth don't use this architecture anymore, because they cannot replicate the entire database and the entire application logic, okay, in order to increase the scalability of the system. I mean, if you think about Spotify, I mean, they have billions of users around the world. I mean, or Netflix. Okay, it's even worse, because I mean, streaming the videos is even more expensive. I mean, we cannot think about the fact that Netflix replicates the entire database many different times. So what they do, they replicate the services. Okay, then they implement this microservice-oriented architecture that allow them to scale the system in terms of services, not in terms of data. But that's that's another course. Okay, if you're interested, I'll wait for you next year. I teach this service-oriented system course. The monolithic, I mean, you have a monolithic architecture, then you also have a monolithic code base, okay? And this can be very bad for development velocity, as said before. I mean, the bigger the size of the system, the bigger the problem in dealing with this, with the code. There might be complete lack of isolation between the different features, because all the features are in the same code base, and then they might be really tightly coupled each other. Okay, and then it's very difficult to move towards a distributed software architecture in that case. Then. A good benefit from moving towards separating front-end, back-end architecture. There's more fine-grained scalability, okay, because the two components can be scaled independently. You might have the web server providing the user interface, can be replicated, okay, independently of the database, for example. You have a separation of concerns, as we discussed last time when we discussed this layered architecture. Okay, this is a layered architecture. Then we inherit all the same benefits from what we discussed last time. But of course, there are also some challenges. So the interaction between these components are very much more complicated than just method calls, as in the monolithic version. Okay, because I mean monolithic version, everything is in the same code base. Then you have only a method call. Here, since you have a different code base, then the two subsystems interact each other by means of network. Okay, and then this is there is communication. And as said before, communication introduces latency and introduces also complexity in managing, understanding the different interaction. Sometimes the developers need to write and maintain several types of clients, okay, for accessing the backend. For example, that's the case nowadays when we have many different types of devices. Then you need to implement an app for iOS, an app for Android, an app for your desktop Windows version, Mac OS version, and Linux version, and so on and so forth. Okay? Well, unless you make it in JavaScript and run everything on the browser, but that's not always the case. Okay, then sometimes, I mean, if you want to let people to interact with this backend, then you need to implement many different client-side applications. And then I say that, so the third way is something that we will discuss next year. So then the aim, okay, the supreme aim is to stop writing legacy code. So, okay, so the question is, how can we stop doing this? Well, you cannot stop it. I mean, whatever you make today will be legacy tomorrow. Okay. Then the only thing that we can do is to be proud about our legacy. Okay. So we cannot stop making legacy system, but we can make a high quality legacy system. Then to ease the working of next generations. Next generation are ourselves in few years, or our son, or whatever. Okay. So the aim of this lectures, and then I would say this course as a whole, is to produce software that we are proud of, okay? And for doing this, we just need to build software that has a value. That's something that we pointed out during the introduction lecture. Okay, so the aim for us as a designer, as engineers, or just as a developers is to build software that creates a value. And then we can do this only if we apply everything we discussed during the course. Okay, start developing the quality culture, start understanding and measuring the software, and then applying the requirements engineering methods and practices that you learned during the first module, applying all the performance engineering practices that you discussed during the second module, and still design principles, architectural patterns, and so on and so forth. Okay, so that's the aim. No matter if we are producing a greenfield software solution from scratch, or we are re-engineering, re-architecting, refactoring a legacy system. Okay, doesn't matter. We always have to take into account all that things that we discussed so far, and that's what we expect from that you apply in the software engineering project development that we start in a couple of weeks. Okay, so we expect that you apply all the things that we learned during these months. You have any question? Okay, then we are a bit early, but I think you are more than happy about this. So thank you guys, and we will publish the assignment Monday. Okay, and yeah, you will have a week, even more maybe for doing it. Okay, bye.
What kind of assignment will we have?